Namaskaram to everyone. Welcome to series of lectures on finite element method. Today we'll discuss about assembly of global stiffness matrix and load vector. If you remember, in the previous class we discussed about how to write an expression for the element stiffness matrix for two noded one dimensional bar element, and that we had derived from the potential energy expression. So again I am writing the potential energy expression phi, that's nothing but your strain energy and work potential. So I am writing the strain energy as of volume integral of sigma transpose epsilon dV minus volume integral of u transpose to f of dV surface integral of u transpose t into ds and sum of all the point loads acting at different locations in a given body, right? So we have discussed already that this, from this you are getting this strain energy, from the strain energy you are getting your stiffness matrix, right? So from this we got body force vector. So from this we are getting traction vector. So these are point loads. So we discussed about stiffness matrix by using two methods. One is by directly the global coordinate system, that is by using a Cartesian coordinate system, and second we discussed by using a natural coordinate system. Now we will discuss first how we will get body force vector and traction vectors. Again, point loads, wherever that load is acting, at that node we will directly add. So there is no explicit explanation is required for the point loads, but it's some explanation is required for the body force vectors and tractions. So first we will talk about how we can develop this body force vectors for each element. Then we will try to assemble all the elements to get a global stiffness matrix as well as the global force vectors. So first I will talk about body force vector. Body force vector. So this body force vector is nothing but your u transpose into f of dV volume integral, right? You know what is this u? U is nothing but your nq, right? Where n is nothing but your shape function matrix and q is your displacement matrix, right? nq. So if you substitute here, you will get this u transpose, that is nq transpose into f of dV over volume, right? So you can write this one as q transpose into n transpose into f of dV over volume. And we know also this volume, you can write it as a into dx, right? So now if you substitute them, we will get an expression for this body force as 0 to LE over length q transpose into n transpose into f of a into dx. And here you know this f is basically your body force per unit volume, which is a constant value for the given body, and a is the cross sectional area of the given element, right? So now we'll try to find it out what is this n transpose, and we'll try to substitute in that. So we have this expression finally 0 to LE q transpose into n transpose into f of a into dx. Since f and a are the constants, I can take it out. So I can write this one f and a outside, and even q transpose is, it is again a displacement vector, you can take it out. So you'll have 0 to LE n transpose into dx. So now you have 0 to LE n transpose dx. So now it is in your global coordinate system. So we can solve this body force by directly using this global coordinate system. Same time you can solve it by using your natural coordinate system also. So first I'll try to do it by a global coordinate system. Then I'll leave it as an exercise to you to try to solve it by using natural coordinate system. We know what is this n. N is nothing but your n1, n2, which is a shape function matrix, right? So when you're writing this transpose, this is nothing but your n1 and n2, right? And what is this n1 shape function? And you know what is the shape function n1 in natural coordinate system, sorry, global coordinate system. N1 is nothing but 1 minus x by L, and n2 is nothing but x by L, right? So if I write these terms, f of a to, I can write it this form like 0 to LE into n1 dx and 0 to LE n2 dx. Right. Now I can substitute this n1 and n2 in this expression. So we substitute and get f of a 0 to LE. N1 is nothing but 1 minus x by L into dx, and 0 to LE x by L into dx, right? So now we try to integrate it and put the limits and see what is the value we are getting it. So if you do that, q transpose f of a, and you have 1 minus x by L, so I'll get this one as x minus x square by 2L, right? So if you can put the limits for this one as 0 to LE for both the values, right? And this is for first term, and similarly we have the second term, again x square by 2L, again put the limits 0 to LE, right? Now they put the limits and see, if you put LE x, you will get LE, it is 0, so you will get LE here. We'll see in the next terms, we can add them. Q transpose f into a, right? So I have the terms like x, so I'll get LE minus 0 first term, and minus, that is again LE square by 2 LE in second, so 2 LE, right, minus 0. So this is the first term I have. Same, this is also I'll have again LE minus 0 minus of LE square by 2 LE 0. So this LE L get cancelled, so LE square L get cancelled. So if you write this expression, you will get f of a to LE by 2 and again LE by 2, right? So what do you mean by that? If we can rearrange this Q transpose, so if I write this one FA LE by 2, again FA LE by 2, right? So what do you mean by this? Suppose if I am considering here this 2 noded 1D bar element which is having 2 nodes, and if you have a displacement q1 at node 1 and displacement at q2 at node 2. Now if this element is having a body force, it's having, assume it that it's having some body force throughout this element, right? Throughout this element we have a body force F, and we know this body force is F is nothing but force per unit volume, right? Because this body force is acting entire volume of the given body. So if you see here FA LE by 2 and FA LE by 2, that means this force, body force per unit volume, if you multiply with the volume of the given element. So what is the volume of the given element? That is cross sectional area into length of the element. You know, this is the length of your element, and the cross sectional area of this element is A. So that means this is F into AE. LE is the total body force is in this element. Now this FAE LE, half of this body force is actually shifting to, so half of this body force, if you see this FA LE, so half of this body force, that is nothing but FA by LE by 2. So that is shifting to node 1, and remaining half FA into LE by 2 is shifting to node 2. So that is the meaning of here the writing this body force expression, where FA LE by 2. So this value is at node 1 and this value is at node 2. So this is the body force vector for a given element. Now similarly, we will try to write the tractions for the same element. So we know the traction vector, right? Traction vector, the expression, it says that U transpose into T into ds into surface integral, right? So this is the traction force. Sorry, traction force, I mean to say traction force. So U transpose in T into ds. So same, you can write it, U is nothing but N into Q. So U transpose will be Q transpose into N transpose, right? So if you can write this expression, and since here it is a one dimensional, you can convert this ds into again the direction of linear x. So that will be 0 to LE. So this will be Q transpose into N transpose into T into dx, right? T into dx. And now if you observe this expression, and if you observe the previous expression 0 to LE FA into dx. So what is the difference if you see in these two expressions? Only the difference is that here we have F into A, which is a body force multiplied with its cross sectional area, and if you see in this expression, that is T into dx, right? So again this T is constant here, and Q is again, it is your displacement vector, right? Then if you rewrite this expression again, like it will become Q transpose, and you can take it as T out. So then you have integral 0 to NE N transpose into dx. So this, if you see this expression, this one, this term, this is the same term which we got it earlier. If you see in this expression, so if you see here this expression, right? So N transpose into dx. Now also, so only here Q trans F into A is a term because it is a body force, but when you are talking about traction, so again N transpose dx into Q into T. So what do you mean by that? That means Q transpose into this T, if we can write this one 0 to LE into N transpose into dx, again sorry, I will just arrange it. So N1 dx, so 0 to LE N2 dx. This is the meaning. So if you remember what we derived through this 0 to LE N1 minus 1. So what we got, if you can recap and see what we got the expression of this one. The same written here, right? 0 to LE N1 dx, 0 to LE N2 dx. Finally, what is the value we got? If you can see that you got that one as LE by 2, LE by 2. So if I just write this, so I'll get here this expression as LE by 2, LE by 2. So essentially I can say that Q transpose, that is T into LE by 2 to T into LE by 2, right? So same here, if we can take the same element to node 8, right, in node 1 and node 2, and if Q1 Q2 are the displacement sets node 1 and 2, and now if it is subject to a traction T, which is nothing but your surface force traction T, and if we see that length of this element as LE, right? So then the traction force total will be T into LE, and this T into LE again, half of this is actually shared with the node 1, that is T into LE by 2, and half of this will be shared by T LE by 2. So that's how whenever you have a tractions on an element, the half of the traction force is shifted to node 1 and half to the node 2, as we have seen in body force, right? So this is how you can write this traction vector. So this is your element traction vector. And when you talk about point loads, wherever we have a point load, we'll just add it up. So that we'll see in the final matrix, we'll just add them in that expression. So now we got body force, we got tractions, we got stiffness matrix also. So if you write this entire potential energy expression phi, so where we got this half, so I'll write in the first expression, then I'll try to give. So volume integral of sigma transpose epsilon into dV minus volume integral of U transpose F into dV the surface integral U transpose T into ds and summation of all the point loads at different points acting on the system. Now you know from this what we got an expression. We got this expression as half Q transpose into KE into Q. And here we got this expressions as Q transpose into, I can write it this one as Fe, body force, and again Q transpose into traction as Te, and this one as Q transpose into your point loads. So if I write this entire half into Q transpose Ke into Q minus Q transpose of Fe, Te and Ps, right? So where is Fe is the body force and Te is your traction force for a given element, and let me write this is also PA. It is a point load acting in that element. So generally point load, it acts only at the nodes, right? So this is how I can write the entire potential energy expression in terms of your stiffness matrix, in terms of this forces, right? So if this is for one element, right, and if you want for the total potential energy for the entire system, for entire system, right, then what you have to do, the total potential energy, you have to write it as summation of this half Q transpose K into Q minus of summation of this Q transpose into F of E, T of E, or it is plus P of E. So if you can write it overall, you can write this one as half of Q transpose K into Q minus of Q transpose into F, where this Q is nothing but your global displacement vector, and this K is nothing but global stiffness matrix, right, where this F is your global force vector, right? And it's easy to write, but how we'll get this global displacement vector and global stiffness matrix and global force vector? When we have number of elements, how we can actually combine them? It is not like a direct geometric addition that you have 1 plus 2, you will get 3. So there is a procedure how we can actually convert the sum of the global elements, element stiffness matrix into a global stiffness matrix. So that we will see now. So now I am taking a simple case to understand. So I am taking a stepped bar which is having some cross section and length, and again you have a cross section and length, again have a cross section and length. So let us assume it that this is L1 and this is your L2, length of the second step, and this is L3 length, and each one is having its cross section. Maybe this is, let me take A1 and A2 and A3. So that means A1, A2, A3 are the cross sections of element 1, 2 and 3. Same L1, L2, L3 are lengths of element 1, 2 and 3. And let us take this material properties for the each step is different. So length, so Young's modulus for the first step is E1, Young's modulus for second step is U2 and E2, and Young's modulus for third step is E3. So I can write this one E1, E2 and E3 are Young's modulus of element 1, 2 and 3. Each one is having. And now let us take, so these are all the geometry and material properties I have sent. A1, area and length, these are the geometric properties or the geometric values of a given system, and E1, E2 are the material properties of a given system. Now let us see, it is subjected to some kind of forces, right? Some kind of forces. Let us assume it that it's having a body force F. Body force per unit volume. Body force per unit volume F for the entire, or if you want I can consider that F1 is a body force for the given only for this volume F1, F2 is separate and F is 3, that also you can do it, but for time being I am considering only F is a body force per unit volume. So that means I am taking the weight of that given system. So let us take that only F is a body force acting on the system. Then let us assume some tractions are acting on it. T1, T2 and T3 are tractions on element 1, 2 and 3. So body force is there across this entire system, that is your F. So that means F is there throughout, and you have a traction. So let us take a traction. Here it's acting like a T1, and here the traction may be T2, and here the tractions T3. Tractions are acting on that, and assume it that here a point load is also acting. At P, a point load P is also acting. So P is a point load acting at node 2. So let me take this one as your node 1, and this is node 2 and node 3 and node 4. So we have total 4 nodes and 3 elements, right? So this is the entire description of a given system. Now I want to convert, I want to first assemble, first I want to know the stiffness matrix, element stiffness matrix of each element, and element body force of each element, and element tractions and point load. Anyway, wherever the point load is there, they will act. And after getting the elemental level of stiffness matrix and body forces and tractions, then we can assemble all together to convert into a global stiffness matrix and global load vector. So if you remember, we know what is the stiffness, elemental stiffness matrix for a two-noded 1D bar. So if I am considering for the each element, element 1, 2 and 3. So we will write the element stiffness matrix right? For the each element we'll write, then element body force vector, then element tractions vector, right? So we'll write it for all. So before writing these expressions, one important thing, you have to always first you write a element connectivity table, right? Because here we have elements. If you see this, we have the elements. If you see here node 1, so before this we don't have an element, but if you see node 2, the node 2 is connected with element 1 and element 2 as well. Similarly, node 3 is connected with element 2 as well as element 3. So that's why it is very important that first we have to write this element connectivity table. So from that it's easy how we can actually assemble them in a simple manner. So if you write this element connectivity table, so let us write element number, then here we write nodes, right? So we can write this table like this, and each element is two nodes, so I can write node 1 and node 2, right? So how many elements we have in this? If you see, we have 3 elements, so I can write this one as first element, second element and third element. So we have total 3 elements, so we can write this entire element connectivity table like this, right? So these are the nodes we have. So element 1, if you see what are the nodes are there in element 1, if you, this is your element 1, element 2 and element 3. So element 1 are having nodes 1 and 2. So I can write this as node 1 and node 2, right? And if you see element 2, element 2 is having nodes 2 and 3, and element 3 is having 3 and 4, right? So my first element in first node in element 2 is 2, and second node is 3. Similarly, my third element, so first node is 3 and second node is 4. So this way you can first I can write element connectivity table. So you will understand that in first element you have only nodes 1 and 2, in the second you have nodes 2 and 3, and in third you have nodes 3 and 4. So once you have this element connectivity table, then you can write element stiffness matrix for element 1, element 2 and element 3. If you remember element stiffness matrix, so if I take element 1, so I'll have element stiffness matrix K1, that is the cross sectional area of that element into this Young's modulus of the element upon the length of that element, 1 minus 1 minus 1 1. So this is for element 1. Similarly for element 2, I can write it as cross sectional area A2 and Young's modulus E2 and length L2, 1 minus 1 minus 1 1. Same for element 3, that is K3 A3 E3 by L3, 1 minus 1 minus 1 1. So this way I can write element stiffness matrix for 3 elements. Similarly I can write element body forces, element body force vectors. If you remember, we have the body forces in that. If you see Q transpose, Q transpose is a displacement vector. So rest we have as a body force. So for the body force F1 is nothing but F into A1 into length of the element by 2, F into again A1 length by 2. Right. Similarly for second, F into A2 into L1 by 2, sorry, L2 by 2, and F into A2 L2 by 2. And for F3, again F into A3 L3 by 2 into A3 L3 by 2. If you remember, when we considered first element, we said half of that body force will go to node 1 and half of the body force will go to node 2, right? Same in the element 2, half of will go to the first node and again half to the second node. Element 3 also half to the first node and half to the second node. So entire we have a body force F, so that multiplied with the volume of that element, right? So that will give the total body force within that element, so that half of it is shifting, right? So that way we are writing the element body force vectors. Similarly, you can write element traction vectors, right? We have T1. If you remember what we have in that T, in tractions we have given separately T1 and L1 by 2 and again T1 L1 by 2. Same tractions also half to the node 1 and half of the traction to the node 2. Same, it is T2 L2 by 2 and T2 L2 by 2. See here I write the traction 3 that is T3 L3 by 2 T3 L3 by 2, right? So that means if you observe this, so when you have this body force, half of that first element body force we are shifting to node 1 and node 2. Same half to this. Similarly tractions also, right? So that's why we got the tractions, element body forces, element traction vectors, both we got, and element stiffness matrix. So once we get all this, then we can assemble them together, right? So how we assemble? And here one important thing, when you are writing the stiffness matrix, it is important to understand the stiffness matrix is for this element 1. This element 1 is having nodes 1 and 2. So that means the stiffness matrix when you are writing, so this element is for node 1 and this is for node 2. And here also in the stiffness matrix, this element is for node 1 and node 2. Because in the element 1 we have nodes 1 and 2. Similarly, if you want to write it for element 2, in element 2 we have nodes 2 and 3. So this means this is 2 and 3. Similarly, for element 3 we have 3 and 4, 3 and 4. Right? And if you see body force, it is on node 1 and node 2 for the first element, and it is for node 2 and node 3 for second element, and node 3 and node 4 for third element. Tractions and same way in element 1 node 1 and node 2, and element 2 node 2 and node 3, and element 3 node 3 and node 4. So that means this body force will go to node 1, this to node 2 in the first element, right? Similarly, in the second element, this body force will go to node 2 and this is to node 3. Same manner, the other values also will be shifted this way. So once you got this, now one important observation you have to do in this entire stepped bar system, how many nodes are there? How many nodes are there? So if you observe it, 1, 2, 3, 4. Total we have 4 nodes, right? So here an important understanding of size of the stiffness matrix. Size of the stiffness matrix always depends upon the number of nodes we have in that given system, whether it is in a system or an element. If we take the first element, we have 2 nodes, and at each node we have only 1 degree of freedom, because we are trying to see it in a one dimensional, that is in x direction. So at each node we have 1 degree of freedom. So that means total we have 2 nodes and each node we have 1 degree of freedom. That means we have only 2 degrees of freedom. So your stiffness matrix size, it depends upon the total degrees of freedom in a given element. So for the element 1, the total degrees of freedom is only 2. So that's why if you observe it, the stiffness matrix size is 2 by 2, right? The size of the stiffness matrix is 2 by 2, and same is the case for element 2 and element 3 as well. So that's why 2 by 2, this is also 2 by 2, right? And if you consider the entire system, how many nodes are there? 1, 2, 3, 4, total 4 nodes, and degrees of freedom at each node is 1, because we are trying to see it in only one dimension, that is in one direction, x. So the total degrees of freedom of this entire system is only 4. So that means if we want to find the stiffness matrix for the entire structure or entire system, which we call it as a global stiffness matrix, we will have a size that is 4 by 4. So when you assemble it, you have to take care that when we want to make an assembling matrix, that is K, right? K. So you have to understand that the size of this final assembled stiffness matrix, and which we call it as a global stiffness matrix, should be a size of 4 by 4, right? So if I write this, the global stiffness matrix K is summation of element 1 and some 2 and 3, right? But you have to understand how we add them. It is not just K1, K2, K3 directly add, right? So we'll see here how we can write this assemble stiffness matrix, or we call it as a global stiffness matrix. K, right? So I'll write this K. We know first size, the size should be 4 by 4. So I'm taking a matrix, right? So maybe 1, 2, 3 and 4. I'm just trying to write this size because the size should be 4 by 4 matrix, right? And I can write these terms also here. Again, this is 1, 2, 3 and 4. So go back to expression here. We have A1, E1, L1, 1 minus 1, 1. Here A2, E2, L2, 1 minus 1, 1, right? So let me take this A1, E1, L1 into inside. Then the stiffness matrix will be like A1, E1 by L1 minus A1, E1 by L1 minus A1, E1 by L1, again A1, E1 by L1. So that means if I say element 1, so the element is this, right? So that is nothing but A1, E1 by L1. So if I go to my size, here it is 1, its corresponding column and row. So here I have to write the value, that is A1, E1 by L1. Similarly, here it is, if you see, 2 and 1. So A1 minus A1, E1 by L1. So if I write this expression, that is 2 and 1, means second column and first row, I will have that value as minus A1, E1 by L1. Sorry. Similarly, if you see first column, second row, minus A1, E1 by L1, right? Similarly, second column, second row, A1, E1 by L1. So I am writing here. So I am getting here A1, E1 by L1 and minus and A1, E1 by L1. This way, whatever I have the element stiffness values, I put it in your global stiffness matrix, right? Same if you can see for the element 2. Element 2 you have, that is in the second row, second column and second row, and again third column and second row, and again in this second column and third row, and third column and third row. So these values again you put it in that your matrix here. So this is second column and second row here. So here you are adding up your values of element 2. So element 2 we have the values, that is A2, E2 by L2, and again minus A2 E2 by L2, and here again at third you have A2 E2 by L2 and A2 E2 by L2. Right, if you can see 2 by 3 and 3 by 3, 2 by 2. So that's where you are getting all these values. And second column, third column, second row, third row. So you have to fit all these values in. Second column, third column, second row and third row you have to fit. Right. And if you observe it here, A1 E1 by L1 plus A2 E2 by L2. That it happening at node 2. At node 2. Why? If you observe it carefully here, node 2 is the connectivity node between element 1 and element 2. Right. So that's why at node 2 you have the influence of element 1 as well as element 2. So that's why if you see here, you are having A1 E1 by L1 which is from the element 1 at node 2 and A2 E2 by L2 which is from the element 2 at node 2. So that's why you are getting a sum of the values here. Right. So wherever you have the connectivity, there you will get the sum from the previous element and from the next element. Right. Same if you can help me out for writing out element 3. So those are at third column and fourth column and third row and fourth row. Right. So if I write it this one, this is third column, it is fourth column and third row and fourth row. So if I write it here, I will get this expression as A3 E3 by L3 minus A3 E3 by L3, and again here I will get minus A3 3 by L3 and A3 E3 by L3. A small change I will do. Erase. This is not 3. So let me put it as so this is 3 and 4. Again 3. If you see, observe it here. Again third node. It is a connectivity between element 2 and 3. So that's why you are getting at here. If you observe it, here you have the values again. Right. I hope you're understanding. So that's how you will get this global stiffness matrix. And what about these terms? Here we don't have any term, right? And here also we don't have any term. Here also we don't have. Similarly, here we don't have. So wherever you don't have terms, so that you make it as zeros. Right. That's how you will get the global stiffness matrix. So now couple of points you have to understand when you talk about global stiffness matrix, right? So first thing, when the size of this global stiffness matrix always depends upon the total degrees of freedom of a given system. Since here we have 4 nodes and each node we have only 1 degree of freedom, so that's why the total degrees of freedom of a system is only 4. That's why you are getting the size of the stiffness matrix as 4 by 4. So that is the first important point you have to understand whenever you talk about stiffness matrix. Whether it is a global or at element level, it is applicable. If it is a stiffness matrix, these properties are applicable. First, the size of the stiffness matrix depends upon the total degrees of freedom of a given system or a given element. Right. Second one, if you observe it, the stiffness matrix is always a symmetric matrix. Whether it is a global or whether it is a element stiffness matrix. Now it is a global stiffness matrix. If you observe it, it is symmetric. If you see this one, A1 minus A1 E1 by L1, the second column, and if you see again minus A1 E1 by L1, and third element is 0 and here it is 0. Again fourth 0, it is 0. So it is a symmetric matrix. And if you observe it in the previous case also, see all the element stiffness matrix also, 1 minus 1 minus 1, it is a symmetry. Right. So the stiffness matrix are always symmetric matrix. That is the second one. The third one is that stiffness matrix are always banded matrix. So we have discussed already what is a band. So that means you have the values along this diagonal. If you see here, this entire if you see this diagonal, this is your diagonal, right? So you have some values, just above or below this diagonals, right? So along this diagonal, so to the degree it is extending the values, if you see, so it is extending, values up to here, right? So this is called the band, right? And below and above the values are 0. So that's why we call this one as a banded matrix also. And the advantage of this banded matrix is that the computation time will be less. You can arrange this one in a different way, but if you arrange in such a way that the matrix is a banded, so that your computation time will be less and your performance will be better. So your results are more accurate in less time. So these are the three important properties of any stiffness matrix. So once we understood this stiffness matrix, global stiffness matrix, so if you want to write this global force vector, right? So it's having body force, tractions and point loads, right? So we know how to write body force vector and traction vector, and point loads just you have to put it where our nodes are there. So if you take this body force, we have already derived, we have this body force vectors, right? So for F1, that is for element 1, and F2, that is for element 2 and element 3. Similarly, we have the traction vectors also, T1 and T2, right? So now we will try to assemble and solve. So you know now how many nodes are there in this entire system. 1, 2, 3, 4. So the total system we are having total 4 nodes, and each node we have only 1 degrees of freedom. So if you want to write this body force vector, you will write that is 4 by 1, because you have only total 4 nodes. So if you write this, you will write this body force vector for all elements, right? So that will be having 4 by 1. Similarly, if you want to write for the traction vector for all elements, we will have again 4 by 1. And point source we had wherever it is there. So if you sum it of all this, you can write this total body force vector as F. We know at element 1, what is the body force we have? F1A1 by F1A1L1 by 2, right? So again at node 2 in the element 1, F1A1N1 by 2. Similarly, if you can see here, observe it, again this 2, node 2, again you are having F1A1 by F1A1L1 by 2, and same time FA2L2 by 2. So that's because again they're all connectivity, because at node 2 you have the connectivity of element 1 and element 2, right? So same is the case for node 3 also. Again you have the connectivity between node 2 and node 3. So if you write that expression, we can write this one as F A1 L1 by 2 F A1 L1 by 2 F, it is at node 2, and F A2 L2 by 2 and F A3 3 by 2. So these are at the nodes 1, 2 we have, right? But when you talk about at node 2, it is at node 1 F1 A1 by 2, and again F1 L by 2. But when you are talking about this node 2, we have the body force because of this F1 A2 L2 by 2, right? So that to be added to this node 1. So I will write this one as F A2 L2 by 2. So we will have that one. And again at node 3 we have, if you observe it here, at node 3 we have again F2 F A3 L3 by 2. So you can add that also here. So we will add this one F A3 L3 by 2. So that way you will get the entire body force vectors. So that means wherever you have the connectivity of nodes, we have the body force of previous element and this means element 1 and as well as element 2, right? And again at the connectivity at node 3 we have for a element 2 as well as element 3. And if you observe it here at element 4, sorry, at node 4 we have only element 3, and similarly at node 1 we have only element 1. So that's why if you observe the values, at node 1 you have only F1 A1 by L2, again at node 4 you have F A3 L3 by 2, but whereas at node 2 and 3 we have this value. So it is for node 1, node 2, node 3 and node 4. So same way you can write it for the tractions as well. If you write for the tractions, so you have T1 L1 by 2, right? Again T1 L1 by 2. This is for node 1, sorry, element 1, it is node 2, and again at node 2 you are getting from element 2 also. So that way you will get T2 L2 by 2, right? And at node 3 you are getting from T2 L2 by 2, and again you are getting from the third element, so that is T3 L3 by 2. And at fourth node we have only T3 L3 by 2. So that's why you can write it as traction this form. Again here also same, because of the connectivity at node 2 you have 2 values, and again at node 3 you are having 3 values. Now if you want to write complete global force vector, so you can add it of all together, which we have added for this body forces and as well as tractions. So if you can add them, you will get the both values, right? That means we have F A1 L1 by 2, this is because of body force, and you have traction T1 L1 by 2. So these are the forces at node 1, and node 2 F A1 L1 by 2 element 1 and F A2 L2 by 2 by 2. So these two combined is the body force, and you have T1 L1 by 2 plus T2 L2 by 2. So these are the tractions. And at node 3 we have F A2 L2 by 2 plus F A3 L3 by 2. These are the body forces, and you have T2 L2 by 2 plus T3 L3 by 2 together. And at node 4 we have F A3 L3 by 2 body force plus T3 L3 by 2. So this all together is nothing but your body force and tractions. And if you observe it, wherever a point load is there, because these are the total forces at node 1, and these are at node 2 and node 3 and node 4, and I already told you. So this is because of body force is traction, and these two are because of body force, these two are because of tractions. And if you observe our initial geometry, and we are given a point load P at node 2, right? So now straight away you go to this global force vector, and at node 2 straight away you can add that point load P, right. So that way body forces, tractions and point loads all together you are considering into the pictures. So that way you will get the global force vector. So once you know global stiffness matrix K, and if you get global force vector, then you can write this entire expression which you have Q transpose K into Q transpose into F, which is nothing but your potential energy. Then you can apply the boundary conditions and you can find it on the stable position for the system by getting a minimum potential energy, that is d pi by dq, and equate it to 0. Then finally you will get the term that's nothing but your kq minus f is equals to 0. It's nothing but kq is equals to f, and where this k is nothing but your global stiffness matrix, where f is your global force vector. That's why these two are very, very important. Finding out the global stiffness matrix and global force vectors. Once you know this global stiffness matrix and global force vectors, then the unknowns are nothing but your q's. These q's are nothing but your global displacement vectors. So we'll try to find it out, this unknowns q, right. So once you know the q, that means you got the displacements, right. Once you got the displacements, then you can find it out strains, right. Once you get strains, you can find it out stresses. So that's how this entire finite element method first begins with finding out at element level, then convert them into global level, then find out the displacements, from the displacements find out the strains, then find out the stresses. This way any complex problem, if you convert them into elemental level and get the elemental stiffness matrix and elemental force vectors, convert them into global stiffness and global force vectors, then solve it, then you can get the displacement values. So this way you can solve any complex geometry in finite element method. Thank you for your patience.